Good day and welcome back for the third part of our discussion on differentiation formulas. In the previous videos, we've introduced various formulas related to differentiation, and specifically relevant to our starting point in this video, I want to remind you of the power rule that allows us to differentiate x to a power. The power comes down front, the new power becomes one less. And then we also saw this kind of sum difference formula. Just like with limits, we can take a derivative of a sum and break it up as the derivative of the first function plus the derivative of the second function. That is, get it into its easier to handle kind of individual pieces. And naturally that makes us wonder, what about products? What about quotients? And to get us working towards the derivative of products, I wanted to start off with what might be the simplest possible example of interest we could consider, which would involve just x's raised to some different powers. So for example, we have f of x equals x cubed, g of x equals x squared, and remember, by properties of exponents, when you multiply those together, you would get x to the fifth. So let's just note to the side, x to the a times x to the b is x to the a plus b. And it never hurts to remind ourselves of some of those algebraic properties. And if we were meeting face-to-face this semester, the typical question that I would ask you is to make a conjecture. Let me just write this kind of down towards the bottom of the page, but if you were to differentiate f times g, do you have any intuition maybe as to what you would expect this to be? And if so, great. If not, well, let's kind of just see what happens with this nice concrete example. And what happens with one example isn't going to tell us what happens in general, but it could give us a good idea of what not to expect in general. So let's just calculate a few derivatives here for fun. So a few very quick applications of the power rule is going to tell us that f prime of x is 3x squared, g prime of x is 2x, and in this case the derivative of f times g is the derivative of x to the fifth, which is 5x to the fourth. And all I want us to do is just make a very simple observation. The derivative of f times g is not f prime times g prime. So note, in terms of this specific example, what we have observed is f prime x times g prime x would be 6x cubed, which is not equal to 5x to the fourth, which is the derivative of f times g. And this indicates to us, if we want to come up with a more general formula, as we've alluded to below, to differentiate the product f times g is going to be more involved than just multiplying their two derivatives together. And this, in fact, leads us to something which is called the product rule, which is as follows. So if f and g are two functions that we can differentiate, the product rule tells us the following. The derivative of f times g is going to be the derivative of f times the function g plus f times the derivative of g. And I think this is maybe a bit simpler to write down using our prime notation. And in words, I would think the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. So as claimed, there's a bit more going on than we might have expected at first glance, and this is what we refer to as being the product rule. So let's go ahead and take the product rule and apply it to this specific product. Now, there's more than one approach. You could, for example, expand this all out and get it in terms of just being a polynomial, i.e. constants times powers of x's, and then use our previous work. And you could certainly do that to double check if you would like. I instead would like to use this as an opportunity to just illustrate the product rule in action. So in terms of the product rule, if we want to make the comparison above, we kind of have our first function f and our second function g. And in words, the product rule tells us we take the derivative of the first function, and I'm just writing out what the product rule tells us, and then we multiply that by the second function, plus the first function times the derivative of the second. And at this point, I have simply written out precisely what the product rule tells us. And I know there's going to be a temptation, especially in the beginning, to try to skip this step and just immediately write it out. But I will warn you, and I will warn you multiple times, up through our first exam, whenever you use the product rule, or in a few minutes here, the quotient rule, I need to see this intermediate step where you write out simply what the product rule tells you. And before you complain, I know I oftentimes will get pushback from students. They'll say, well, why would I write that out when I can just jump to the conclusion? And my response is typically, if it's an easy step for you to write out, those could potentially be the easiest possible points you get on an assignment. And I, of course, prefer that positive spin on it. So now that you've shown me that you have applied the product rule, what remains are hopefully two simpler derivatives that we need to evaluate. And this is exactly what we discussed at the end of that previous video. We can just go through using kind of our power rule and that sum difference rule. So in that first derivative, the 4 comes down front and the new power of x is 3. And remember, the derivative of a constant is 0. And note, if you don't want to write the 0, that's perfectly fine. I'm going to write it just so we see where that term went when we differentiated it. And yes, you can certainly write 2 times 4 is 8. But I'm going to leave it as is. Times the function x to the 4th plus 3x squared plus 7. Plus, and note I'm just kind of cutting and pasting until I get to the derivative portion. And now going term by term using the power rule, we'll have 4x cubed plus 3 times the derivative of x squared, which is 2x to the first, plus the derivative of a constant, which is 0. And I'm going to leave it exactly in this form. Note, we're going to get it to the point where we have calculated all of the derivatives, so we've answered the question that has been asked. And do not worry, there will be plenty of opportunities this semester to simplify. It's just in these problems I really want us to focus the majority of our attention on the calculus. But I will note that if you prefer to take it further and simplify, you are more than welcome to do so. But just be warned, if you simplify and make mistakes as you go along, you will potentially lose some small percentage of points. Now that we've seen the product rule, let's go ahead and think about how we can differentiate a quotient. So that would be the derivative of f divided by g. And similar to the product rule, it doesn't work out maybe as naturally or as intuitively as one might expect at first, but there's a bit more going on. And the quotient rule tells us the following. For the derivative of f over g, I'm going to think of f as the top or the high function, and g as the low function. And when I first learned calculus, I had a professor that had kind of a phrase that she would mention as she went through the quotient rule, and it's something that's really stuck with me. And it is as follows. So low d high minus high d low all over low squared. And if you prefer to write this in the prime notation, I think it's a bit simpler to get out here. F over g prime would be low d high minus high d low all over low squared. And just a quick kind of cautionary warning here. When it comes to using the quotient rule, we have a difference of two quantities in the top. And remember, the order that you subtract most definitely matters. So you have to be very careful with the quotient rule to ensure that you get that correct order. And now that we've seen the product rule and the quotient rule, we are in a perfect position to practice a few examples. And what I would like to suggest is that you, as usual here, pause the video, take 5 or 6 minutes, and go ahead and calculate the following two derivatives. So assuming that you have done so, let's go ahead and start with the first example. It's a derivative of x squared over 1 plus the square root of x. So this is something that's ideal for the quotient rule. We have a top function f and a low function g. And once again, remember, whenever you use the quotient rule or the product rule, I need you to write out an initial step illustrating that rule being used. So in this case, the quotient rule tells us that we take low d high minus high d low all divided by low squared. And a nice thing about writing this out is hopefully you won't make a silly mistake that you may make if you try to do everything in your head, but also it allows us to very conveniently see how this is broken down, leaving us two hopefully simpler, easier to evaluate derivatives. So just working our way from left to right, the derivative of x squared is 2x, and the derivative of 1 plus the square root of x is 0 plus 1 over 2 square roots of x. And recall from a previous video in this section, the derivative of the square root of x using the power rule is 1 over 2 square root of x. And this is something that we encounter frequently. You most likely just want to make sure you are familiar with this formula. And we're dividing by 1 plus the square root of x quantity squared. And as mentioned in the previous example, you certainly could do some amount of algebraic simplification, but once you get it to this point where you've shown me what the quotient rule is doing, evaluated those remaining derivatives, I do not need you to simplify any further. When we need to simplify, we will, but for now, I really want to focus in on kind of mastering the differentiation portion. Moving on now, for this second and remaining example, hopefully you rewrote this a bit algebraically first. Now, there are several options. You most certainly could just expand this out all the way into a polynomial and use the power rule. Or, since we were talking about the product rule, I'm going to go ahead and use that. So if we think about writing this as the derivative of x squared plus 2x times x squared plus 2x, this is certainly a scenario where we can use the product rule. So we would take the derivative of the first, so we're writing this out because we're using the product rule, times the second, plus the first times the derivative of the second. In terms of those derivatives, note they're both the same, so we can do this quickly and efficiently using the power rule. So from left to right, the derivative of x squared is 2x, and the derivative of 2x is 2. Multiplied by x squared plus 2x plus x squared plus 2x times 2x plus 2. And as mentioned before, leaving it in this form is most definitely okay. Now note, there's also an alternative way to do this. we could note that x squared plus 2x quantity squared, if we just algebraically rewrite the function before we differentiate it, would be x to the fourth plus 4x cubed plus 4x squared. And that's simply by, you might think, foiling it out. And once you've foiled this out, now we can differentiate term by term using the power rule. So 4x cubed plus 4 times 3x squared plus 4 times 2x. And if you were to go ahead and simplify those two quantities, you would find that they are equal to each other. And I want to finish with just one more observation to kind of plant the seed for something that we will see in a couple sections. But this is a very important observation to make. So note, if f of x is not equal to just an x, then we cannot use the power rule to differentiate f of x raised to the nth power. So that is to note, we could not have directly applied the power rule to the quantity that we see here. But do not worry, later on we will have another rule of differentiation that very conveniently applies to this scenario. So you'll have to stay tuned. So take care.